All right, so let's begin. Thank you very much for staying this long in this course, even though I think we all know that to learn anything a bit more advanced or worthwhile, you have to, try to stay on for more than a few lectures to be able to start seeing that how things are progressing, or to begin to get some handle, or at least get an idea of the topics that are going to be covered or that are being covered. So hopefully from today you will be able to get a better idea of how quantum algorithms work. Yesterday we discussed a very simple quantum algorithms that is called Deutsch-Jozsa algorithm, that just has a Hadamard transform and then a phase oracle and then Hadamard transform. And we saw that how with one query of that phase oracle we are able to tell whether the function is a constant function or if it is a balanced function. So that algorithm shows sort of a couple of things. The one was that quantum algorithms can give us a speed up over classical algorithms, because to know what the function is in a black box, classically we have to give that function at least n by 2 plus 1 queries. If we have to decide whether the function is a constant or a balanced function. So there's another algorithm that actually has the same circuit, but the function that is implemented in the black box has a secret string in it. So the function is such that when we give an input to that function, it multiplies the function with a secret bit string and then gives at the output the sum of that product. And our job is to guess that secret bit string. And classically, we have to give at least as many inputs as the number of bits to that circuit to be able to find that secret bit string. But using the same circuit as the Deutsch-Jozsa circuit, but with a different phase oracle, we can find that bit string with just one query of that function that multiplies secretly with a bit string. That algorithm is called Bernstein-Vazirani algorithm, and I will discuss that in detail, which is similar to Deutsch-Jozsa. But today I first want to focus on a completely new algorithm, which is called Grover's search algorithm, and I'll come back to Bernstein-Vazirani algorithm in the next lecture. Just because that's a fascinating way of seeing how quantum computers work. But Grover's algorithm is actually really important in that sense that number one, it triggered sort of it helped trigger the race for building quantum computers in the 90s, along with the Shor's factoring algorithm. So these two algorithms that showed a quantum speed up over classical algorithms, they both helped this race towards building quantum computers that we are just seeing now, to sort of getting to a maturity, or at least to a stage where we will finally be able to say, hopefully in a couple of years, whether quantum computers can really be built with a very high fidelity for all the qubits or not, because of all the progress that has been made. So, but Grover's algorithm is actually important in another way as well. Today we will see that how quantum computers are different from classical computers again, and hopefully your ideas about quantum computers will get another boost, and you will see that how quantum algorithms and their design is different from classical algorithms in terms of thinking. And just to repeat, classical algorithms sort of work in the same way as we think about things in everyday life. For example, I gave an example last time that if you have to tell someone, let's say to tell a robot to do a certain job, you can program the robot, okay, raise your hand, walk to that distance, and then pick that stuff up and then come back. So this sequential sort of thinking is behind the classical algorithms. I know that there are improved versions like machine learning, etc., but ultimately everything in terms of the computer execution, it works in this sense. But quantum computers, as we saw yesterday, they are sort of different. And the difference comes from the ability to process superposition of states. For example, in the Dijkstra's algorithm, we saw that by initializing all the qubits in the zero state and then performing a Hadamard transform, which is just Hadamard gate on each qubit, we are able to get a state which is the equal superposition or uniform superposition of all possible combinations of bits for that number of inputs. And then if that input is given to an oracle or anything, so an oracle is just one thing, but any circuit or something that process information, that can now process information on this superposition state instead of performing operation on each combination one by one as we do classically. So that's where quantum speedup comes from this, the ability to process superposition states. Of course, we saw some drawbacks when we were implementing it physically, that we have to do run the circuit many times, thousand, maybe several thousand times, and that number actually increases with the number of bits, and the speed up sort of seems to be getting lost because we have to run the circuit many times to be able to find the output state, because output state is also a superposition state, and quantum mechanically we cannot access the superposition state. All we can access is the collapse of the superposition state to different possible measurement configuration. For example, at the output it could be 000 or 010 or 011 and so on. So we have to make a lot of measurements of the identically prepared system and then prepare a histogram to be able to see what was the output state. However, the trick is that people are planning to use quantum computers for those problems where the speed up is still retained even after performing these many computations. And then there is actually an even better way of working with quantum computers, where we can get this speed up by working around this dilemma of performing a lot of computations repeatedly. For example, when in the next week we will see how the quantum Fourier transform works. And when we will have an algorithm for quantum Fourier transform, we will see that it's polynomially better than the classical fast Fourier transform. So we have fewer number of steps. However, the output of the Fourier transform is also a superposition state. And if you really just interested in Fourier transform, you actually can't get much speed up, because the advantage that you get in terms of computing the Fourier transform, you lose that advantage when you have to measure many times because you want to find the output superposition state. So, however, still quantum Fourier transform is a critical ingredient of algorithms, because some people have learned ways to use the Fourier transform state without measuring it as an input to something else, and that something else has at the output maybe only few bits, so that you have to measure a very few times or maybe only one outcome, and then you don't have to measure again and again to access the superposition state, because you are feeding the superposition state into another algorithm that has at the output maybe only one or two possibilities, so that you only measure a couple of times and what the output is. So we will get to that algorithm in the next class, but today we will discuss the Grover's search algorithm. So this algorithm, let me start sharing my journal. So this Grover's algorithm actually is a very simple algorithm, and it shows many things. So let me Grover's search algorithm, and the purpose of algorithm is search through an unstructured data set. For example, you have some items, some numbers, some names, some strings, or anything in a database, and the database is unstructured. So it's not sorted. If they're names, they're not sorted. If they're numbers, they're not 1, 2, 3, 4. They might be 5, 3, 2, 10, something like that. So they're unstructured, that there's no structure to this database. So classically, if we have to search through this database of, let's say, something that contains n entries in it, we have to perform, in the worst case, n operations on this data set, because we might be, uh, looking at this item and see if this matches our search criteria. For example, this database is a database of books, and we are looking for a book on quantum computing. So we will go one by one, that will check if this is a quantum computing book. No, we will go to the next one, we will go to the next one. If we are lucky, it might be the first one that we see. But if we are, lucky on the average, we might be, able to find that quantum computing book after roughly half of the entries in this database have been exhausted. But if we are really unlucky, that quantum computing book might be the last one that we will pick up to see if this book is quantum computing or not. So when we, compare complexities of different algorithms, just for those people who are not from computer science background, we always work out the number of steps or number of operations for the worst possible case. That's how we compare different algorithms. So for the unstructured data set, the worst possible situation tells us that we have to perform at least, so in this case, actually, even at least doesn't matter, because there are total n entries. We have to perform n searches of this data set. And we will see that quantum mechanically, using Grover's algorithm, we will be able to find an entry that we are looking for in only n square root number of operations. That if this is a database containing a billion, let's say a million items, like 10 power 6. So classically, you will need 10 power 6 searches of this database, but quantum mechanically, you will only need 1,000 searches. So if this is, so you can just see that this square root advantage is a big advantage in terms of searching through the database. So that's why, many searching companies right now are interested in implementing these quantum computers, because this search operation has become such a vital thing to do in this age when there's a lot of data around. So this algorithm is the one that we are going to analyze today. And to make our life easy and to make the problem independent of what that search space is, it could be, a search space of books, or it could be some websites, or it could be some other data set, etc. So to just get rid of all of that thing, we, simplify the problem in this sense that, let's say, we assign a number to each item. And we just, so instead of now searching for the items, we will just be searching for this number. But this number is linked to the item that we are trying to find out. So we can forget about that thing, how the number is related to the particular thing, because that would be changing with each different data set. If they are book, so these numbers would be related to some books. If there are some other data, they will be related to something else. But that's a trivial thing, okay? How to map the given data sets to some index cards. And the search criteria for our purpose, for this algorithm's purpose, can be defined as like this. So search criterion is that we have, some way of telling that whether a number is a solution to this search problem or not, if we construct some, black box, and let's say we call it some phase oracle, and it implements a function such that if the number is our solution, let's say this 101 is the book that we are looking for, then it will multiply it with a minus sign. Okay, so whatever this number is, let's say this is some x, so this goes to minus x. So, and if the number that we are looking for is not a solution, it will simply go out at the output as it is. So we have some machine, some access to a function that works like this. So we have access to a function f of x that maps numbers n bits number of binaries, like it's a combination of 0 1 and their n bits to either 0 or 1. And we have implemented this function f in this phase oracle, which means that our input x is being multiplied with -1 power f of x into x. Now, if this f is 0, which means that our input x is not a solution to our search problem, it will be transformed to x again, because f0, so -1 power 0 is 1. And if f is 1, which means that for a given input, and let's call that given input some w, for this w, f w is 1, so this w is transformed to -w. So it means that this part of the problem, which would be different from one problem to another problem, that which thing we are searching for, what is the criteria, or some labeling of the things that we are going to search. We have now relegated it, all of it, to this black box. And in this black box is the function implemented, which is able to recognize whether a given thing is what we are looking for or not. And for the purpose of analyzing the algorithm, we have said that it is some function f which maps the input x to -x if it is a solution, and if it transforms it to x if it is not a solution. Okay, so now that we have defined our problem, let me first just give you the circuit that Grover discovered. So I'm just to clarify, the word circuit that I'm using, it's synonymous with algorithm. Most of the people working in quantum computers are using circuit model to represent algorithms, which is less common in classical computers. Mostly classical algorithms are given in terms of a flow chart, but quantum algorithms are mostly given in terms of a circuit. So when I say circuit, it really means an algorithm. So this algorithm that was discovered by Grover, I will first just tell you what the algorithm is, and then I will show that why this algorithm works or how it is working. Okay, so Grover discovered that if you initialize a bunch of qubits to 0 state, and then you performed a Hadamard transform, this Hadamard transform really is the bread and butter of quantum computing. They show at a lot of places. And once you have these Hadamard transforms of all the qubits, you feed it to a phase oracle, which have access to your unstructured database, and it implements a function f that transforms in a way that I just talked about. That if the input state corresponds to the item that we are searching for, this would be transformed to minus of the input state, and if the input state is not a solution, it would be transformed as it is. So once you pass through this phase oracle, then we take the Hadamard transform again of all the qubits, and then we implement another phase oracle, but this time this function has nothing to do with the database. This is just a notation for a part of a circuit that we are going to call oracle, just because it has a similarity to this oracle, but this oracle has nothing to do with the database, and it has this f naught is nothing to do with this function. So I'll just later describe what this oracle is. And then you perform the Hadamards again. And then you perform the measurement. But before you perform the measurements, you might have to repeat this part of the algorithms many times. It might have to be repeated r times. And we'll compute how to compute how many times this has to be repeated. And then you perform the measurements, and at the output, you will have your index of that thing that you are trying to search for. All right, so let's now analyze that why it works, and how to see that it really, is what it is, what we are saying that it is. So for that, let me, start with this zero step. So at the zero step, we have this zero state. So initialize the psi naught is this zero state, which is just, a symbol for this, or I hope that you remember that this really means this. It can also be written as like this. So there are several ways. But once we pass through the Hadamard gates, let me call this state some S state. So this S is nothing but the Hadamard applied to this zero state. And we know that it should be 2 power n sum over some x equals 0 to 2 power n minus 1. And I'll just explain this notation. So this x. Okay, and just to recall, this really means this. By the way, let me just label this capital N as 2 power n. So this states really mean this, that let's say 0, 0, sum this state, and all the, possible states that are out there. And in literature, there is actually another way of notating these states, and this is this, that some people would just write it like this: 0, 1, 2, 3, all the way to n. So where this index that we have assigned to different states just corresponds to the decimal conversion of this binary strings. So in this case, this S state, when I write it like 0 to n minus 1, x, you can picture it like this. But this really is this state, the one that I just wrote above, that these 0, 1, 2, 3, they're all, binary states. But this is just a convenient notation, that instead of, writing it like this, that we say, okay, x naught goes from 0 to 1, x1 goes from 0 to 1, and xn minus 1 goes from 0 to 1, x naught, x1, x2, all the way to xn minus 1. So really is this is the representation that we have all the binary combinations in the S state, but it's convenient to write it just like this, where we have introduced this decimal index x that goes from 0 to n minus 1, and this index x in the state is representing these states with this decimal notation. So anyway, this is the state S at this stage, where it's just going to be fed into this phase oracle. And let's now see what this phase oracle does. So the second part, phase oracle, or you can call it Groover oracle. So this has a function. This implements a function from n bit to 1 bit. So f of x goes from this n length string of 0, 1s, and answer is either 0 or 1, in such a way that when we have some input x, it is transformed to minus 1 power f of x into x. So it's a phase oracle, so it works with minus 1 power phase, which really means is this, okay, that if, let's say, W is your solution. So out of all of the possible, states 0, 1, 2, 3, all the way to n, some state, let's say number 10 or something else is your solution that you are looking, is your search item that you're looking for. So in general, let me label it with W. So W is your solution that you're looking for. So it means that X is then transformed to X if X is not equal to W, and W, which is the solution, is transformed to minus W, because f of X is 1 when X is your solution, and f of X is 0 when X is not your solution. This is how we have prepared this mapping, which really means is this, that this phase oracle UF implements this functionality, that X goes to X if it is not solution, and it goes to minus of itself if it is a solution. And just, to distinguish X and W, I have used W for solution and X for non-solution. So let's now see how we can, represent this phase oracle in operator form, because I will have to, work out how this state is transformed after passing through oracle. So I can write this oracle UF very easily like this, that it should be written like this. Oh, sorry. That W is transformed to minus W, and X is transformed to just X if X is not a solution. So it means that this operator UF, which represents this Grover phase oracle, is just this thing, because if a state W is applied to it on this right side, WW would be 1, because this W and X are orthogonal. W is one of the state and X is all other, and since all of these states, these 0, 0, 0, 0, 0, 1, 0, 0, etc., they're all orthogonal state. So if any of them is W, for example, this is W, this is orthogonal to all other states. So I can write this phase oracle in operator form like this, because when W will come, WW would be 1, and I'll get minus W, because the X into W would be 0. And if X comes in, any X, and that would be, so this W into X would be 0, and X into that particular X would be 1, and we will get X. Let me just, write it a bit more explicitly. You should think of this like this, that some index I that goes from, let's say, 1 to n, other than that this index is not equal to the index of solution. So you just exclude that solution state, and that solution state is over here. So any X that comes from the right side will be transformed to X, and any X that is a solution will be transformed to minus X. So let me write it actually even more explicitly like this. So let's say this is some state X naught, some X1, all the way to X n minus 1, X n minus 1. And there's one other state which is missing from here, and let's call it some W state. So it's over here. So all these states that are not solution, they are with positive signs, and all the states that are solution are with negative sign. So when this is applied to W, this will be transformed to minus W, because WW is 1, and W with all other X's is 0, and we will get minus W. And when this, instead of W, we have X over here, any X, let's say some X1. So if this is X1, so X naught into X1 will be 0, Xn minus 1 into X1 will be 0, W into X1 is 0, only X1 into X1 would be 1, and I'll get X1 at the output. So it means that this operator represents our phase oracle that just gives a minus sign to an index, which is solution. Okay, any question about this oracle? All right, if not, let me rewrite this oracle in another way. And that is that if I add this W state over here as well, and I have to subtract it as well, so this will simply becomes sum over all x, 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 and another W would be added here, W, W. So what I did that I just added this missing term over here so that this sums become over all x, where over here this was all terms other than this x, and so this because I added another term W here, so that W would have to be minus. But adding all of this number here simply means that I have an identity to W, W. So it means this phase oracle can be written like this. Let me give you another way of thinking about this oracle. Perhaps that will help you. And that's actually how we will implement it in the notebook as well. That I can think of this, oracle like this. It's a matrix that multiplies all the input states with one which are not solution, and only that state, for example, if it is this is 1 0 0 0, this multiplies with 1. If it is 0 1 0 0 state, this multiplies with 1, and so on. Only one state which is a solution will be multiplied with minus sign. But this operator can be written like this, that I can write this minus 1 as 1 minus 2. So if I write it 1 minus 2, I can have this identity matrix here, but then I will have to have 0 0 0 minus 2 0 0 0, and all other elements are 0. But now this becomes identity, and this is nothing but minus 2 W state, because this is a state that corresponds to this W state. So this oracle can be thought of as this matrix as well. All right, so now we have our oracle operator, and let me write our S state again, which was just before the state is going to be inputted to the phase oracle. So this is X. So this now notation simply means that sum over all possible X. All right. Now I am going to rewrite this state S in another way, that let's separate out that term which is not equal to W, which is a solution from this sum, and write it separately. Okay, from this S state, I have just written the W state, which is solution, separately. So this is now a sum over all X other than W. And what I can do is multiply with n minus 1 here, n square root. So this 1 over n minus 1 square root here, X not equal to W over X. And now this thing, this part, if you see, this is a state which is perpendicular to W, because this doesn't contain W, and W is perpendicular to all of these. So this is a state which is perpendicular to W. And by multiplying with n minus 1 over here and n minus 1 over here, I have normalized it as well, because there are only no n minus 1 terms in this sum. And if I divide it with n minus 1 square root, this is a normalized state. So I can call it, let's say, W perpendicular. So now I get n minus 1 n square root W perpendicular plus 1 over n square root W. I still haven't applied my Grover operator. I'm just rewriting state as in terms of a component which is solution and everything else which is not solution and which is orthogonal to this. And if you like, you can visualize this thing, in sort of this imaginary plane that is spanned by this, vector W perpendicular and this vector W, and your state S lies somewhere over here. And by the way, I can see right away that this square and this square, they add to 1. You can check. So its square and its square adds to 1. So it means I can represent them using some cosine and sine functions. So let's do that. So let's say that this is some cos theta by 2. And this is some, this then must be sine theta by 2. And there's a reason for choosing theta by 2 instead of theta, because theta, it's twice appears somewhere else as well. So this cos theta by 2 is n minus 1 n square root, and sine theta by 2 is 1 over n square root. So I can say that this is theta by 2. Remember, this is not strictly true because these w's are complex numbers and I can't really, draw them in a plane, but just to, get an idea that how it can be visualized. And this visualization is very helpful. Okay, so now I have, written my state S like this or this. Now I'm ready to apply my operator UF. Okay, so let's see what UF into S gives us. This UF was identity minus 2 WW into, let me use this representation. This would be a bit easier. So this is n minus 1 n square root W perpendicular plus 1 over n square root W. Okay. All right. So when this identity applies to this, this comes out as it is. When this identity applies to the second term, it is still the same. And when this minus 2 WW applies to this one, this would be 0 because W into W perpendicular product is 0 because they're both orthogonal. So this product goes away. And when this W applies to this W, this is 1. And I'm left with minus 2 over n square root W. So WW1 and only W is left, and this minus 2 over n square root, which I can further write as n minus 1 over n W perpendicular. And this plus 1 over n square root minus 2 over n square root can be combined to get minus 1 over n square root. So this is my state UF into S. And if you compare it with this state, this is nothing but with only a sign flip from plus to minus. So it means I can visualize it like this, that this is some cos theta by 2 W perpendicular minus sine theta by 2 W, which means that this is W perpendicular, W plane, W. So if this was S state making angle theta by 2 with this W perpendicular vector, this UFW state is a state that is flipped around this W perpendicular axis. So this is UFS, and now this angle is theta by 2, simply because of this minus sign. So this is this can be interpreted as having a negative angle with this omega perpendicular axis. All right, so it means that this oracle in the Groover circuit can be thought of as just flipping the input state around the W perpendicular axis. All right, so let's now talk about this part. And for this part, instead of working through each layer individually, let me just first work out this whole part as one term, and then I will apply this one term over whatever the output is available here, because this then gives a very nice visualization to what is happening to the input state. So, and this part is, by the way, called the diffuser. So this part where we have H into UF naught, this is called diffuser because this sort of diffuses the state. So let's see what this is, and I'll now also show what this F naught is. This is part of the algorithm. So this UF naught also implements a phase oracle, but with a function f of x that goes from an n-bit input string to either 0 or 1, but this is 0 if x is 0. Just make sure I'm not, sorry. Apologies, the notebook closed, and I hope not everything is lost. Okay, unfortunately, everything is lost, but that's okay. So I was talking about this diffuser, which is Adamart's UF naught, Adamart's, and this UF naught implements a function f naught of x from an n-bit string to a 1-bit output of either 0 and 1, such that if the input is 0, then the input 0 means that the input is 0000 string, then the output is 0, and if the input is any state other than 0, the output is 1.
I'm sorry, sir, but we can't see the notebook.
Oh, sorry. Okay. All right, thank you. So we were talking about this, diffuser circuit, and this implements an oracle UF naught with function f naught of x, such that this f gives 0 if the input is 0. So if over here all bits are in 00 state, so we get the 0, f naught is 0, and if x is not 0, if this input is not 0, it gives 1, which means that a 0 state is transformed to 0 because f is 0, so -1. So in general, this is a phase oracle, so it always works -1 power f of x. So now f naught is 0 when x is 0, so we get 0 to 0, and for all other x's we get -x, because for any x other than 0, f naught of x is 1. So if f naught is 1, so -1 power 1 is minus, so it becomes this. So if you want to visualize in terms of the matrix, this is like this: 1 -1 -1 -1 -1 -1. By the way, this is equivalent to saying this -1 1 1 1 1, because this this is a global phase, so only the relative phase matters. So either you multiply the 0 state with -1 and all other with +1, or you multiply 0 with +1 and all of the -1, it's the same thing. But we'll stick with this thing for now. So if this is this, I can write this matrix like this. So let's say I just multiply this also with -1. So -1 -1 -1, and then I will have to add 2 here and 0 0 0 0 all the way. So this is nothing but minus identity plus 2 times 0 state, because this index represents 0 0 state. Or I can write it like this: 2 0 0 minus identity. So this operator has nothing to do with the search space, because this is fixed. This multiplies only the 0, 0 state with a number different than other states. So this has nothing to do with the search space, this F naught. All right, so let's now see what this combined circuit does. Okay, and I can work out this combined circuit very simply. And let's call it, some operator V. So this is Hadamard, UF naught, Hadamard, because we have Hadamard on both sides. So let's, substitute for UF naught. This is 2, 0, 0 minus identity Hadamards. So this Hadamard will come here and here as well. So 2 times Hadamards on 0, 0, and Hadamard from this side minus, this is identity. So we will have Hadamard, Hadamard, but we already know that Hadamard square is identity. So this becomes identity. And this thing we already know. We computed initially that when we have input 0 and we apply Hadamard, we call this state S. So this is also S bras. So this is S cat. So this is identity. So it means that this diffuser circuit as a whole just implements this part, 2SS minus 1. All right, and this will make our life bit easier, because I can now work out this V very easily, that I can put the expression for S over here and expression for S over here, and then multiply them all together. So what we will get is this cosine square theta by 2. Remember, this S was cosine theta by 2 W perpendicular plus sine theta by 2 W. So this, when you make a product, so you will get this final result plus 2 sine square theta by 2 WW. And I would encourage you to work it out for yourself. 2 cos theta by 2 sine theta by 2 WW perpendicular plus W perpendicular W minus I. So when I just substitute SS here, I just collected the product terms over here. So now I have this V operator, and let me apply this V on this UFS state. And this UFS state, if you recall, was cosine theta by 2 W perpendicular minus sine theta by 2 W. Now, once you substitute this operator V here and multiply all the terms, and just remember one thing, you only have to remember one thing, and that is that W is 1, W perpendicular is 1, because we constructed these W perpendicular as normalized state, and W perpendicular is 0, because these are orthogonal. So using these facts, you can work out these terms, and I'm just going to write the final result, which is this cos theta plus theta by 2 into W perpendicular plus sine theta plus theta by 2 into W. So this is after applying this V operator on this thing. Let me now construct a visualization for you again. So we have, let's say, this imaginary plane spanned by W perpendicular and this W. So we had this S state prepared after the first Hadamard, and then this made an angle theta by 2. And then when we applied the UF circuit, UF operator on S, we flipped it around this axis, so the angle became this and the state came here. Now, After applying this V part, we see that this state has gone to this state such that this whole angle now is theta plus theta by 2. So it means that this angle is just theta. So this is after applying V and UFS. So it means that all that the Grover circuit did was this, that initially, let me just write in a single line. So we applied Hadamard's of n bit. So this prepared S state. So we started with the 0, and then we had this oracle UF, and then we had Hadamard's again, and then an oracle UF naught, and then Hadamard again. So what this UF did was flipped this state around W perpendicular, and what this V did was actually that it flipped this state around this S state. Okay, because this is theta by 2, this is theta by 2. So if you flip it around this S state, so this angle is theta. So when you go back here, so you go with you go to angle theta with S state. But even more than that, we can have another way. So when we started our search state, this S has some projection along W perpendicular and some projection along W. W is our solution, but it is mostly inclined towards W. It means its component along this W perpendicular is much more than its component along this W state. And when we applied this UF and this diffuser V, so this is diffuser V, we shifted the state from S to this state, that we increased its angle towards W. Now its projection along W is greater than its projection before, and now it is more tilted, rotated towards this solution state. So it means that if we keep repeating this step, that if instead of applying this 1 times, let's say I apply it R times, such that each time it rotates a little bit more towards the solution, then in the next cycle, this will actually go here, add another angle theta. You can work it out. In the next cycle, it will add another angle. So slowly we will reach close to this axis. So it means that we need to multiply and need to apply this combined circuit R times, such that R theta plus theta by 2 is pi by 2, because this angle is pi by 2. So we want the state to rotate to this W state. This color is not cool. Let me change it. So from here I can compute this R as, so if I take this theta common and divide it over there, so this becomes pi over 2 theta, and this is half, so this becomes minus half. And this theta is nothing but, if you remember, it was 2 sine inverse 1 over n square roots, because if you remember, sine theta by 2 was 1 over n square root. So if I take sine over there, 2 over there, so this is 2 sine inverse 1 over n minus half, and this is pi over 4 sine inverse 1 over n square root minus half. And if n is large, I can approximate it like this, that pi over 4, this sine inverse will be approximately 1 over n square root, and n square root can go up, and this is this. I can even ignore this half and pi by 4. These are just trivial term. So the number of times that we have to apply this whole Grover circuit R is proportional to n square root instead of n that we see classically. Okay, so any questions so far? All right, so let me give another sort of recap in a few minutes, and then we'll discuss the notebook implementation. That we had a state prepared S in a superposition state, and then the UF rotated it around this axis, and then it was rotated back around s-axis, but in general we try to rotate our state in the space of states towards the solution space, and that's how actually quantum algorithms work. And that's why their thinking is different. We have to think about quantum computers as something that we are working with states in a Hilbert space, and we are trying to construct unitary operations that we need to transform the state towards the desired state by some operations. So that's why the thinking for these algorithms is somewhat different. Actually, you can think about this particular problem in somewhat different way as well, because we had this s state like this. So s was this. So if you think about x, all possible combinations had one equal amplitude. So it means the probabilities of x now of 0, 1, 2, 3 and all n state is the same because they have the same amplitude. Remember, s is 1 over n square root sum of all x states. So you can think that we started with this state with all indexes with equal superposition, but when we apply the UF operator, so what UF did? So UF actually did this, that it flipped that state which was solution. Suppose this was the solution state, so it kept everything else the same, but only flipped the state that was not the solution, because it just marked the index which is a solution. And then once we applied this diffuser V, it takes it back, but then the amplitudes of these states decreases and the amplitude of this state increases. I'm just exaggerating. So this is the action of V, that it increases the amplitude of the state that is solution. That's why our this state is inclined more towards this W, because this has a higher amplitude for this W. So you can see it from here as well. The amplitude of all state W's is sine theta plus theta by 2, and W is our solution. So when this theta increases, this sine increases. So amplitude of W has increased, but W perpendicular, which are not, which is a superposition of states which are not, our solution, they are given by cosine. So when theta increases, cosine decreases. So that's why, you can think about this diffuser as this. And overall, this, Grover algorithm is sort of the amplitude amplification of a state which we are looking for. So this amplitude amplification is the way of thinking about quantum solutions. That in general, when we have a superposition state that contains everything, the thing that we are looking for and the things that we are not looking for, and we have to come up with an algorithm that selectively amplifies the probability amplitude of that state which you want at the output, and suppress the amplitudes of those states which you don't want at the output. So that's how we generally think about quantum algorithms. Any questions? If not, let me show you the Kisket implementation, and for that, let me share my computer screen. All right, so we have to move this around. Okay. So I have already shared this, notebook with you, and the first input is just importing different things like this operator, quantum circuit, etc. And let me execute this one. And in the next circuit, you see I have defined the phase oracle. And I hope that you can see that this definition of phase oracle is very easy. And I'm now introducing in this notebook another way of thinking about quantum algorithms, and that is that you can put different parts of an algorithm into functions, and then when you call those functions into your main algorithm, you can reduce clutter, that you can group different parts of a circuit into one box, and just you can label the box as well yourself. So just as we define functions in other programming language, we can define these functions for these quantum circuits as well. So now so this def is a way of defining functions in Python. So I'm defining this function phase oracle, and it has a name. So the name is fixed as oracle if you don't give any name, but if you give a name, it will keep that name as oracle. And then this is a bit more general program, that this is written for a situation that you can even have more than one solutions. So if there are more than whatever the solutions are, those are the indexes that we want to mark. And then you see, I just have this oracle matrix as an identity matrix with the 2 power n entries, but the indexes that I have to mark as negative, they are being marked negative, because whatever the list that we will send here to mark these indexes with negative, I'm just iterating with this variable index over this, and then those entities of this identity matrix are being marked -1, which either correspond to my solution. Okay, and then this is a way of converting a matrix to a unitary operator, because in the circuit we have to have everything in operator shape. So this command operator can convert this oracle matrix, which is just a matrix, into this unitary operator. So it's like this. And then I have this diffuser circuit. Diffuser circuit is very simple. This is also a function that takes n qubit as an input, and then it has this quantum circuit, which I'm calling diffuser, giving it a name. And then it has Hadamard transform on all the qubits, and then it has this phase oracle with the 0 index as marked. So I'm just using the phase oracle, the Grover phase oracle, for this UF0 operation as well, because UF0 and the Grover phase oracle are the same, except that in the UF0 the 0 index has to be marked. Okay, so it's -1 and then everything as 1 1 1. So when I will use this phase oracle here, this will prepare a circuit like this. So this will prepare a matrix -1 1 1 1 1. So this is UF0. So I know that I use this -1 1 and this +1, but it's the same thing. We can have this -1 and everything else plus, or this +1 and everything else minus. So this is just that UF0, and then I have Hadamards again, and now this is a function again. And then I'm using Grover as a function again as well, to use it again and again for different things. So this is just a circuit of n quantum bits with n classical bits as well now. And to call this function, I will be giving the number of qubits, and I will also be giving the index of the elements that we have to mark negative, that we are searching for. And then this R is something that we are going to work out, and I'll just show how to compute this R. Actually, we have already computed it. We have already seen it, that this R. Okay, so this R is exactly equal to this, or actually this is exact equivalence, and this is approximate. So for one solution, you can use this formula to compute R, that how many times this circuit has to be repeated. When we will have mu solutions, mu number of solutions, then there a mu square root comes here, and I'll discuss it later how we can work out that. But for now, let's say for when there are mu number of solutions, if mu is equal to 2, there are 2 solutions. If mu is equal to 3, there are 3 solutions. So this mu comes over here. So with this expression, we can compute R. So then I'm computing this R. And once I've computed this R, I'm just printing this thing when we call this function to see what we have given as input. And now this Grover circuit has Hadamard's on all the gates to prepare S state. And in step 2, I perform all times this, this phase oracle and diffuser on my this state S. So this is a bit funny way of, in Python, I'm using this underscore as also a variable, which sometimes people do when they're not going to use that variable in the program per se. But let's to be a bit less dramatic, let me use I. So this I is not being used anywhere. I'm just all times applying this phase oracle and this diffuser on my quantum circuit, and I'm using this append command to append these circuits. And at the end we have these measurement operators. And so it's this, let's say this is the circuit with the 3 qubit, and there are 2 solutions, number 3 and number 4. So number 3 corresponds to 011 and 4 corresponds to 100 state. So if you execute this one, you will get this circuit. This means that R is 1. There are 3 qubits, 2 states are marked, and R is 1. And so, and this is oracle and this is diffuser. And I'm first, executing it with the simulator, and see my output is 011 and 100 with 50% probability, which tells me that I have 011 and 100 as solution. Okay, and you can use the quantum computer as we discussed yesterday, that you if you haven't already done, you import your token here, and then you load your account with this command. And for this circuit I used Athens. I'm not going to execute it now because it takes a lot of time. I have already executed it to show you the results. Now when I ran this program for 1000 times, this is the result that I got. And you see, even though my solution is 011 and 100, I'm getting the probabilities, non-zero probabilities for other states as well, simply because the quantum computers that are available right now, they're very noisy. When they start the circuit in 00 state, they're not really, some of the qubits are not really in 00 state. And when we are performing different operations on those qubits, some operations, are not performed exactly. And also there are measurement errors and many other types of errors that results in this, very bad histogram. But the hope is this, that soon quantum computers would be good enough that these 2 lines would be standing up, pretty good. And just to, show you another aspect, to increase my confidence in these measurements, I increased my number of circuit runs from 1000 to 8000. And now you see, it hasn't improved really that much. I'm still getting high probability for this 3 state and 4 state, but still other probabilities are also, getting very close. So sometime doing a lot of, measurements doesn't really get rid of the errors that are creeping up in the currently available quantum computers. But I hope that you don't get deterred by the noisy quantum computers that are available to general public in the cloud right now. Hopefully better quantum computers are coming in this year and the next year with more qubits that we can use. Okay, so any question regarding the algorithm? Let me show you just one more example. Suppose I'm using a 4 qubit circuit and I'm still marking this 3 and 4. So now you see my circuit is being implemented with the 2 repetitions of oracle and diffuser, oracle diffuser. And if I just run this thing, so again 011, this is 3 state, and 10100 4 state, they are being shown with high probability, and all other states are coming with smaller probability. And you see, even though this is a simulator, I'm still getting non-zero probabilities for other states. And that is because, let me show this thing, that in this Google algorithms, there's no guarantee of getting to the final results with 100% probability, there is some, there could be some errors in the final result, and that is because of this thing. You see, we start from a state in this at this angle theta by 2, and when we perform our operation, it's going to flip this state by another theta, and the second operation might take the state here instead of exactly taking at this point. So this might be theta, or it could happen like this. So let's say we started from here, theta by 2. After one operation, we go to this. So this is theta. After another one, we go to this, another theta. After another one, we go to this. This is theta. But now this is, less than theta by 2, or maybe, if this is less than theta by 2, we stop. So it means that we may not always be able to, get this state exactly aligned with this state. So the probability of finding this W is 1 minus sine square theta by 2, because when this is this close, the probability of finding this W is cosine, square of this angle theta by 2, and probability of error is this. So this cosine square theta is actually 1 minus sine square theta by 2. So probability is not 100%, simply because we are rotating with this discrete number of angle theta, and we may not exactly align to this W state that we are looking for. So there, our final state could be within this interval of theta by 2 on one side and theta by 2 on the other side. Okay, so is there any question regarding this algorithm? If not, let me quickly, in a couple of minutes, describe what would happen if there are more than one solution in our database that matches our description. So it means that our UF operator will have, multiply marked elements. So in this case, our S state can be written as, let's say there are some mu number of solutions, and we have to sum over some, mu I, some I 1 to mu, and there's this Wi. So now there are mu a number of solutions. So I can, write this, all these Wi states over here, and this would be mu over n square root over here. So this means that sine theta by 2 now will be equal to mu by n square root, and you can work out exactly the same thing with this multiple, states, and you will see that this R is the number of operations are proportional to of the order of mu over n, that n over mu, sorry. And number of operations are proportional to n over mu. So if there are more solutions, of course we should be able to get to the solution faster, and that's how the quantum computer also predict. But this is much faster than a classical computer still, because when you have even like 2-3 solutions in a space of n solution, at worst, in the worst case, you might have to perform n minus mu searches, which is still of the order of n and not less than n. But in quantum computer, the order is n over mu. Okay, Zahur, do you have any questions? Okay. All right, so I hope you are now clear on this, one of the famous quantum algorithms, and also a bit more familiar with how quantum algorithms work, and how to, think about these quantum programs.